As the sun heats the land, air in contact with the land is heated and rises. Air over the water next to it remains at comparatively cooler temperature and flows onto the land to replace the air that has risen. The wind that flows in from the sea is called the sea breeze. It is temperature-driven and will attain maximum strength about mid-afternoon. As the heat goes out of the day, the sea breeze will become gentle towards evening. At night, the opposite effect occurs. As the land cools down, the cool air flows downhill off the land and out to sea to displace the comparatively warmer air over the water. This land breeze, flowing off the land, is usually fairly gentle, just 4 to 6 knots, and does not extend far out to sea, just 5 to 10 miles. A squall is a sudden, sharp increase in wind speed lasting minutes, contrary to a wind gust lasting seconds. They are usually associated with active weather, such as rain showers, thunderstorms, or heavy snow. Squalls refer to the increase to the sustained winds over that time interval, as there may be higher gusts during a squall event. The trade winds are the prevailing pattern of surface winds from the east toward the west found in the tropics, within the lower portion of the Earth's atmosphere, in the lower part of the troposphere near the Earth's equator. In the northern hemisphere, they begin as north-northeast winds at about latitude 30 degrees north in January and latitude 35 degrees north in July, gradually veering to northeast and east-northeast as they approach the equator. Their southern limit is a few degrees north of the equator. The Coriolis effect, in combination with an area of high pressure, causes the prevailing winds, the trade winds, to move from east to west on both sides of the equator across this 60-degree belt. As the wind blows to about 5 degrees north and south of the equator, both air and ocean currents come to a halt in a band of hot, dry air. This 10-degree belt around Earth's midsection is called the intertropical convergence zone, more commonly known as the doldrums. The intertropical convergence zone, or ITCZ, is a belt of low pressure which circles the Earth generally near the equator, where the trade winds of the northern and southern hemispheres come together. It is characterized by convective activity, which generates often vigorous thunderstorms over large areas. The position of the ITCZ varies with the seasons, and lags behind the sun's relative position above the Earth's surface by about 1 to 2 months, and correlates generally to the thermal equator. In January, over the Atlantic, the ITCZ generally sits no further south than the equator. The ITCZ appears as a band of clouds, usually thunderstorms, that circle the globe near the equator. In the northern hemisphere, the trade winds move in a southwestern direction from the northeast, while in the southern hemisphere, they move northwestward from the southeast. When the ITCZ is positioned north or south of the equator, these directions change according to the Coriolis effect imparted by the rotation of the Earth. The position of the ITCZ varies with the seasons, and lags behind the sun's relative position above the Earth's surface by about 1 to 2 months, and correlates generally to the thermal equator. In January, over the Atlantic, the ITCZ generally sits no further south than the equator. In June, over the Atlantic, the ITCZ is between 5 and 15 degrees north of the equator. Where the trade winds are weak, the ITCZ is characterized by isolated cumulus and cumulonimbus clouds. However, where the trade winds are stronger, the ITCZ can span a solid line of active cumulonimbus clouds embedded with other cloud types developing as a result of instability at higher levels. Cumulonimbus tops can reach and sometimes exceed an altitude of 55,000 feet, and the ITCZ can be as wide as 300 nautical miles in places, presenting a formidable obstacle to transit. The ITCZ appears as a band of clouds, usually thunderstorms, that circle the globe near the equator. In the northern hemisphere, the trade winds move in a southwestern direction from the northeast, while in the southern hemisphere, they move northwestward from the southeast. When the ITCZ is positioned north or south of the equator, these directions change according to the Coriolis effect imparted by the rotation of the Earth. The definite sign of approaching bad weather is the coast radio stations be issuing frequent and regular securite warnings, including the best information available, of the position of the center and its expected movement. An unusually steep fall in the barometric pressure is a clear indication of an approaching low-pressure system. These cirrus clouds followed by cirrostratus clouds are a sign of deteriorating weather. These warning signs are useful, but not conclusive on their own. Significant change in the direction and strength of the wind. Unusually clear atmosphere, remarkable visibility. Extensive high cirrus cloud, swirling in towards the storm center, and reflecting lurid coloring at sunrise and sunset. In the open sea, swell from the direction of the storm center. High humidity and rain increasing as TRS approaches. A boat operating close in along the coast should, upon hearing a tropical revolving storm warning for that area, should proceed without delay to the nearest safe refuge. Port authorities should have TRS emergency plans in place. If you make a report with which you are not familiar, you should contact the port control on VHF for advice. If you enter a safe refuge which does not have a TRS plan, avoid anchoring amongst other vessels if possible. If one drags, it usually picks up a few others. If at sea and the TRS forms rapidly in the immediate vicinity, secure the vessel for heavy weather and head for the nearest safe refuge. If the weather reports do not confirm the weather in your area, advise the coast station and other vessels of the conditions being experienced. Does the area provide shelter from the prevailing and expected winds? Is it easily accessible? Is there sufficient swinging room if you anchor? Is there sufficient depth of water at all levels of tide? Is the safe refuge good holding ground if intending to anchor, or a secure mooring point capable of mooring the boat with chains or wire? What is the distance of the safe refuge from your present position? What is the estimated time to reach the safe refuge in the prevailing conditions? Is it in a likely path of the storm? What will be the effect of a storm surge in the safe refuge? Are there any submarine cables or pipelines that make the safe refuge unsafe?